We have been talking about exponential and logarithmic functions in this chapter. In section 4.5, we will look at some equations, exponential and logarithmic equations. So first, exponential equations. An exponential equation is any equation that has a variable in the exponent. Now there are two types that you are going to see that will require two different approaches to solve. The first type is if you can make your equation look like this, matching bases on both sides with possibly different exponents on them. So I will call this type the matching bases type. Look at these equations that you see here. In the first one, you can clearly see that both have base 5. And this one-to-one property of exponential functions, remember one-to-one means for every output, there was only one input that yielded that output. So if the outputs of an exponential function are the same, b to the x equals b to the y, then the inputs must be the same because an exponential function is one-to-one. It also just makes sense. If 5 to the power 2x minus 1 equals 5 to the power 3x, the only way that can happen is if those exponents are equal. So if in your equation you just have an exponential expression on one side and an exponential expression on the other side, and the bases match, if you have matching bases, then you can just basically drop the bases and just set the tops equal to each other and then solve the equation that you get. In this case, it's a linear equation. I will just subtract 2x from both sides and that's it. We're done. That's the solution. You can check if you want, but it's not mandatory for exponential equations. If I plug in -1 for x in my original equation, on the left-hand side, I get that. And we want to see if these are equal. On the right-hand side, I get that. So 2 times -1, -2 minus 1, that's 5 to the -3. And on this side, we also get 5 to the -3. It checks out. So the solution to this equation is -1. Now, it's not as clear in this next example if we have matching bases. On the left-hand side, the base is 10. On the right-hand side, the base is 1 over 100. They're not the same, but we can make a match. We can make them both be powers, well, in this case, of just 10. So the left-hand side, I will leave as is. And the right-hand side, I will change that 1 over 100. So everything else I'm keeping the same. 1 over 100 is 1 over 10 squared, which means it can be written as 10 to the -2. So we still don't have matching bases. We have to simplify this right-hand side, and that gives me power of a power. We multiply the powers. We get 10 to the -2x. Now the bases are exactly the same. And if we have matching bases, if the bases are exactly the same, then just drop the bases. That's the one-to-one property of exponential functions. If the outputs are the same for this 10 to the whatever function, then those inputs, those exponents, must be equal. So now we have to just solve this equation. This is a quadratic equation. It has the x squared term and the x term, so I have to put everything on one side in order. And then factor, this one factors as x plus 1 or x plus 1 squared. Set each factor equal to 0. It's just a -1 for this one also. And you can check that and you will see that it works. Try this next one on your own first. Pause the video and then let's see if we agree. This is also an exponential equation. I see an x in the exponent. That's what it means for the equation to be exponential. So that immediately you want to look and see if you can make matching bases. Well, the base on the left is 8. On the right is 1/4. They're certainly not the same. But there is a way to write them both as a power of the same base. I can write 8 as 2 cubed, and I can write 1/4. It's 1 over 2 squared, so it's 2 to the negative 2. So I can make matching bases. I can make both bases become 2. I'll just write the left-hand side as 2 to the third, and then to the power x minus 9. This is more than one term also, so I'll put that in parentheses too. And then the 1/4 is 2 to the negative 2, and then that to the power x squared. We'll use the property of exponents that says when you have a power of a power, you multiply the powers. So that gives us 2 to the power 3 times x minus 9. I'm going to distribute that 3, and that gives us 3x minus 27. On the right-hand side, we get 2 to the power of a power, multiply the powers, negative 2x squared. Well, now we have matching bases. And when you have matching bases, you can just drop them and set the tops equal to each other. So now we have a quadratic equation. It has both the x squared term and the x term in it, so we'll put everything on one side. I'll add 2x squared to both sides. And let's see if we can solve it by factoring. The leading coefficient is not 1, so this is not what I call the super easy kind. I have to do the AC method, or you can factor it any other method that you know how, as long as you show all of your work. And b is 3, so I want two numbers that when I multiply I get negative 54, and when I add I get 3. I'll do my scratch work on the side here. I always start with 1 and the number. Some of you may see the numbers right away, but if you don't want to just sit there and wait. You'll go after it. Nope, these don't add up to 3. 2 and negative 27. Nope. 3 goes into 54, so I get negative 18. Nope, they don't add up to 3. 4 does not go into 54. 5 does not go into 54. 6 goes into 54. So 6 and negative 9 gives you negative 54. Oh, they add up to negative 3. We want 3. So I'll just change it to negative 6 and 9. So these don't work, but we got to the pair that works. So we will break up our quadratic. You can also use the quadratic formula, of course. Whatever method works, as long as you show your work. And then here we can factor out a 2x. Here we can factor out a 9. And then the x minus 3 comes out. 2x plus 9. Set each factor equal to 0. We get our two solutions, 3. And when you set this equal to 0, you would subtract 9, then divide by 2. Negative 9 over 2. And you can check, and you'll see that both of these work. Let's look at these next two equations and compare them together. So we have 5 to the x equals 25. On the left-hand side, we have 5 to the x. X is in the exponent, so of course this is an exponential function. The power that I don't have power on this side, but I can make the bases match here. I'll just write 25 as 5 squared. And now I can just set the powers equal to each other. So that one's pretty intuitive too. You ask yourself, 5 to what power gives you 25? The answer is 2. But then you get to this one and you say, 5 to what power gives you 20? So 5 to the first power is 5. 5 to the second power is 25. The answer is somewhere between 1 and 2. I talked about this a little bit in the last video at the very end. So we want to be able to solve this equation too. Of course, you could just rewrite this in logarithmic form, and that would give you x equals log base 5 of 20. And you know that you can use the change of base formula, and the answer could be written as either log or ln of 20 over ln of 5. But sometimes the equations look a little bit more complicated than that. What I want you to notice about this is that it was not so easy to write the right-hand side of this equation as a power of 5. We didn't immediately see 5 to what power gives us 20. So we had to use logarithms to solve the equation. Here are a few equations where we have to use logarithms to solve them. They are still exponential equations because the variable's in the exponent, but they're not that easy kind where you can just make the bases match. This is the one that I just did, but let's see how we can do it using these steps. So first, it's an exponential equation, so it must have something to a power that has the variable in it. Isolate that term first that has the exponential. Then we are going to take the log of both sides, each side. Now it could be log, or you can also take the ln of both sides. Let's just see what happens if we do that. So let me rewrite my equation here. Just leave a little bit space here, and I'm going to stick an ln on both sides. So we're just using the fact that ln, or any log, is a function. So if two things are equal, their ln's are going to be equal. Now, the next step is to use that power law of logs, which we also called the wraparound rule, or bring the cat down from the tree. And that gives us a new equation that is no longer exponential because it doesn't have an x in the exponent. This is actually a linear function. So the next step, it just says continue to solve for the variable. Whatever type of equation you might get, oftentimes it's just a linear equation. So to get x by itself, I'll just divide both sides by what's bothering the x, which is ln of 5. And that is our exact solution, ln of 20 divided by ln of 5. And you can put it in your calculator to also get an approximation. They normally tell you how many decimal places you should go. I'm just going to round to 3 decimal places for this one. And we get approximately 1.861. Again, this is the exact solution. It's before you get any decimals from your calculator. And this is the approximation. Let's do a couple more. We'll follow the same steps. I see that there's an x in the exponent. So this is an exponential equation, which means first thing you want to see if you can make the bases match. There's too much stuff happening here. I don't know if I can make the bases match. First, I'll have to isolate that whole 3 to the x thing. So I'll just cover it up like I usually do with these types of problems. If I just cover this thing up, how do I isolate that thing, that block that you don't know what's under it? So it's just like solving a linear equation. You have to first move, you add the 5 to both sides, and then you get 2 times that thing. Let's remember what that thing was. It was 3 to the x. So you get 2 times that thing equals 12. And now again, I want to isolate that thing. So how do I get that stuff by itself? I'll divide both sides by 2. And that gives me, let's remember what was in here. Whoops. Erase the whole thing. It was a 3 to the x. When you divide both sides by 2, you get 3 to the x equals 6. See, we don't know 3 to what power gives me 6. I don't know how to write 6 as a power of 3 with easy numbers. So this is when we apply log or ln to both sides of this equation. What does that do? Wrap around the x, put it on the side. Make sure you show all of these steps. You know that you're eventually going to bring the x down, and sometimes you get too excited and do it before you're supposed to. No, you have to show all of these steps in this order. So then the x comes to the side. We get x ln of 3 equals ln of 6. Now to get x by itself, we will divide both sides by ln of 3. This is the exact answer. Then you would put it in your calculator for an approximation. And we get approximately 1.631. Here's another exponential equation. Again, we know it's exponential because there's an x in the exponent right there. And there's a whole lot of stuff happening here. The exponential term is the term that contains this 1.23 to the power 2x minus 1. So I want to isolate that exponential first. How do I isolate that? I'll do my trick. I don't know if this helps, but if I just cover that up, I have 20 minus 4 times this stuff equals 1. So how do I get that stuff by itself? I have to first subtract 20 from both sides. And then that gives me -4 times that stuff that was there. Oh, what was it again? It was 1.23 to the power 2x minus 1 equals -19. Now to isolate it, I will, and you have to do this, divide both sides by -4. That gives us 1.23 to the power 2x minus 1 equals 19 over 4. Now you could write the decimal equivalent of 19 over 4, but let's say if it was 19 over 3, and then you have a repeating decimal or something that's not easy to simplify, I wouldn't round. Never round in the middle of a problem. Never round until you are done. Never round in the middle of a problem. So now that I have my exponential by itself, I will take the ln of both sides. And what that does is it's going to bring this whole exponent to the side. It is more than one term, so I'm going to have to put it in parentheses. 2x minus 1 comes to the front here, and then I still have ln of 1.23 equals ln of 19 over 4. What we're trying to solve for is this x over here, and it's just a linear equation. It has these weird looking numbers here, but these are just constants. ln of 1.23 is a number. ln of 19 over 4 is a number. So this is just like if you were, let's say, trying to solve this equation. 2x minus 1 times, I don't know, 17 equals, then some other number, I don't know, 48. How would you solve that equation? You have two options. You can distribute this 17, and then that's a little bit of cleaning, and then move and isolate. But actually, you could also just divide both sides by 17 first to get rid of that, and then move the 1 and then get rid of the 2. And I think I'm going to do that process to solve this equation. We will divide both sides by ln of 1.23 because it's being multiplied by that parentheses. And that gives us 2x minus 1 on the left, ln of 19 over 4 over ln of 1.23 on the right. Now to get x by itself, first I have to get rid of that 1. So I'm going to add 1 to both sides. And that gives us 2x equals that fraction, ln of 19 over 4, divided by ln of 1.23 plus 1. And then to get rid of this 2, we have to divide this whole thing by 2. So there's two ways you can write that. You get rid of this stuff. When you divide everything by 2, you could write this complex fraction, which just means more than one fraction within a fraction. That whole expression on top plus 1 is all on top, and then all of it gets divided by 2. Or if it looks too cluttered here, we could also write it as, instead of dividing by 2, we can think of it as multiplying by 1/2. And this may look a little bit cleaner. ln, oops, I better be careful. It's ln of that thing, 19 over 4, divided by ln of 1.23 plus 1. This is the exact answer. You would put it in your calculator. Now you can do a decimal approximation. Now you can round. And that gives us approximately 4.263. Here are a couple more exponential equations. They're exponential because there is an x in the exponent. This first one might remind you of those quadratic type equations that we solved, the ones that can be made to look like a quadratic equation because they have 3 terms. One of the terms is just a constant, and then the other 2 terms are related in a way that looks like a quadratic equation. The power on the variable on one is twice as big as the power on the variable on the other one. So you look at the powers here, we have the exact same thing happening. There's a constant, there's 3 terms. The power on this one is 4x, which is twice as big as the power on this one, which is 2x. So we're going to do our substitution just like we did with quadratic types before. We are going to let u equal 3 to the 2x. Then 3 to the 4x is just going to be u squared. You can see that if I just square both sides here, u squared gives you the square of 3 to the 2x, power of a power, you multiply the powers, and you get 3 to the 4x. So now I can substitute for everything in my equation. 3 to the 4x has a new name. It's called u squared. 3 to the 2x is called u. And now we'll solve this quadratic equation. Set each factor equal to 0. When u minus 3 is equal to 0, you get u equals 3. This one gives you u equals negative 2. Now we go back and put in what u was equal to. 3 to the 2x equals 3, or 3 to the 2x equals negative 2. So let's look at each of these equations. This one is like the first type of equation we saw in this section. The bases match. The power on the 3 here is 1. So I'll just set the 2 powers equal to each other. 2x equals 1. So x equals 1/2. That's one solution. To solve this equation, I would have to try to write negative 2 as a power of 3, which you probably don't see how it can be done. You can think about taking the ln of both sides, but remember, ln of a negative number is undefined. The domain of ln is only positive numbers. You can also use the fact that the range of 3 to the 2x is only positive numbers. There's no way you can raise 3 to a real number power and get negative 2. So this one doesn't have any solutions. The only solution to this equation is x equals 1/2. In this next one, again, we have these exponential x in the exponent, it's an exponential equation. But you might notice that every factor in this equation, every term in this equation has the factor 10 to the x. So that's a common factor that we can bring out. So this is a combination of an exponential equation. And then when you take 10 to the x out of every term, you get x squared minus x. Oh, I meant to subtract this term first. Okay, let me backtrack here for a second. Let me start over. This equal sign, at first I thought that was a minus also. And we can do that. We can subtract this from both sides so that we have 0 on one side, just like we do with our quadratic equations. All right, now I am ready to take out that 10 to the x. And let's factor this all the way. And we set each factor equal to 0. Well, 10 to the x equals 0 has no solution because 10 to any real number power is going to be positive. That has no solution. So the solutions to this equation are 2 and negative 1. We've seen application problems with exponential functions so far where we just were given an input. So we have the function, and then we were given an input, and then we had to find the output. Well, now that we know how to solve equations, we can also do it the other way around. We have the output, and then we would have to solve for the input, like in this problem. The velocity of a skydiver t seconds after jumping is given by this function, where v of t is in feet per second, so that means t is in seconds. How long after jumping is the velocity 70 feet per second? So this 70 that they're giving you is a number that we would have to plug in for the velocity, which is v of t. So you write the 70 here, and then you copy the function. The unknown in this equation is going to be the t now. We have to solve this equation. Well, this is an exponential equation because the variable is in the exponent. So it's definitely not one of those where you can just make the bases match. So we have to get to that exponential piece first, get that by itself, and then ln of both sides. So in order to get to that, we have to get rid of that 80 first. So I'll divide both sides by 80. And remember, never round in the middle of a problem. So 7 over 8, this one can be written as an exact decimal, so if you want, you can convert it, or just leave it as 7 over 8. 1 minus e to the negative 0.2t. Now again, think about if this was the thing you were trying to solve for, what would you do? You can subtract 1 from both sides. 7/8 minus 1 gives you negative 1 over 8. And I have to get rid of this negative. I'll multiply both sides by a negative. Why don't I just change it right here? These both become plus. So I'll just get rid of that. And now we are ready to take the ln of both sides. Well, the nice thing about having base e is that you don't have to say, oh, I'll just wrap this around and put it in front. Ln of e to anything is just that thing because ln and e are inverse functions. They just sort of cancel each other out. So I get negative 0.2t on the right-hand side and ln of 1/8 on the left-hand side. Now to get t by itself, we will divide both sides by negative 0.2. And that is the exact solution. Of course, it's an application problem, so you want to give an answer that makes sense. So let's put this in the calculator. and we get approximately 10.4, and the units for t were seconds. So the question was, how long after jumping is the velocity 70 feet per second? And the answer is after about 10.4 seconds. So all of the problems that we did where we set up an exponential function, like those compound interest problems, population problems, anything that we had before where we just worked with, here's the input, now find the output, you can now the other way around. They would give you the output and you plug it in, you solve the equation to get the input. As I said, this section is about solving exponential and logarithmic equations. I will cover logarithmic equations in the next video.